On behalf of Space Education and Research Foundation, and on my personal behalf, I welcome Dr. Ritesh Kumar Mishra, the speaker for this webinar today. And today, this webinar is on the evolution of solar system, rather origin and evolution of the solar system. And in this webinar, there will be 5 talks by Dr. Ritesh Kumar Mishra. Today is the first one, which is sort of introductory, and it's entitled as Our Place in the Universe. If I also take this opportunity to welcome all the participants from different countries who have joined us from their places to listen to this talk. And before I hand over the mic to Dr. Ritesh Kumar Mishra, I will briefly introduce him to you. Dr. Ritesh Kumar Mishra was born in a village, Dhawalpur, in the district of Bhagalpur in Bihar. He grew up in different cities in India because his father had a transferable job. So he moved to different places in India and had education in very highly reputed schools like Air Force School, Kendriya Vidyalaya, Sainik schools in Sainik School in Jamnagar, like that, the early education. And his graduation and post-graduation he did from Bhopal and all from Delhi University. He did his MSc, BSc in BSc B.Ed in Physical Sciences at Regional Institute of Education, Bhopal, and MSc in Physics from Department of Physics and Astrophysics at University of Delhi. He did his PhD at Physical Research Laboratory, which is at Ahmedabad, and it is a unit of Department of Space. He also did postdoctoral work at Physical Research Laboratory. In addition to the postdoctoral work at Physical Research Laboratory, he did research work at the Center to Petroleum and Geochemical Research at Nancy, France, and NASA Johnson Space Center, Houston, USA, and at Heidelberg, Germany, in the institute. Beside his very diverse interests in scientific fields, he enjoys reading, writing, and discussions on different kind of contemporary and ancient literature. He is a very good player of different games and sports. He explores to understand the diversity of life living in the present and past times around the world. He is committed towards a sustainable, symbiotic human life. With these few words, I take this opportunity to request Dr. Ritesh Kumar Mishra to start his talk, and I, along with all of you, will listen to his talk. Dr. Ritesh Kumar Mishra, please.
Thank you, Dr. Vats. It's my pleasure to be presenting a few talks and leading a discussion session on our place in the universe. The talk will be basically about the origin and evolution of the solar system. And I have drawn upon the resources from several people. Before I start my talk, I acknowledge all the help, advice, education, learning that I've had from different people at different institutions over the course of my life. And I especially thank Space Education and Research Foundation, Ahmedabad, for giving me an opportunity to present the few ideas and have a discussion with you all at this point of a time. So before I start, let me say a warm welcome to each one of you. So maybe good morning and good afternoon, good evening, depending upon which part of the world you are currently in. And with these few words, I will start the talk. So we live on a planet Earth. Humans as a species on planet Earth have been for around 300,000 years. If you look at life itself, the major explosion of life on this Earth has taken place in the Cambrian era of 542 million years, although our Earth is 4.5 billion years old. So out of this 4.5 billion years of age, only for 542 million years, the complex evolution of life has taken place. However, we are very, very special because in our solar system, as far as we know, there is the planet Earth on which the complex life form as we currently know it exists. And therefore, our interest is to know how come such a planet with such high level of complexity gives rise to such a wide diversity of life. So only if we know the origin and evolution of the solar system can we hope to understand how the life evolves and therefore how we have come to this place, and if there is a possibility that there could be life at other places, not just in our planetary system but in other stellar systems. At this point of time, we pretty much know life only on Earth and as we see it, but our quest is on, and hopefully in another 2 decades or so, we will be able to have a more comprehensive answer to this question whether life exists at several other planets, and if so, how different or how similar it is to the one that we currently see on the Earth. So before we go on to so we need to know how does a solar system form. So what should a viable theory of formation of sun and the planetary system should give? A viable theory of solar system and its origin should be able to explain all the physical properties of the different constituents of our stellar system or of our solar system. Most of them should be explainable by the physical and chemical principles, the laws of physics that are applicable, like conservation of energy, conservation of momenta. The motions of these objects should be governed by, we should be able to explain as to how they have achieved that kind of a motion over a period of time. And this should be generally be explainable for most of the elements that exist on the planetary system. So there are 2 major things that we want to explain. We want to explain the physical characteristics of all the elements like planets, asteroids, and then we should also be able to explain how the diversity in them exists and how that diversity is created. And to be able to do that, we should also be able to tag them to what time did they start with a homogeneous system and develop these kinds of heterogeneity as we see. Heterogeneity in size, heterogeneity in composition, heterogeneity in their position, and how those determine different characteristics as we see today. We will probably then be able to understand how it was in the past and how probably it will be in the future. So first what we will do is we'll look at the main characteristics of our solar system. The main physical characteristics, physical and chemical characteristics of solar system. And then the subsequent talk, we will try to peg them to different times as to how these characteristics, physical and chemical characteristics, were achieved in different point of time, and what do they say about the formation of solar system and what specifically they help us to understand. So let's start with the physical characteristics. So our sun is a typical G2V, G2 class of a normal star in a Milky Way galaxy. If you look at this slide, then the dot represents our solar system, which exists in Orion's spur. So sun is a typical star of mass 2 into 10 to the power 32 kilograms, which exists which we'll say as one solar mass, which exists in the Orion sphere in the barred spiral galaxy, which we call as the Milky Way. So there are different arms of this barred spiral galaxy. Into one of the not the arms, into one of these spheres we exist. We exist about 25,000 light years away from the center of our galaxy, which is about 100 to 180,000 light years in its size. So although our solar system is only about 4.6 billion years old, our galaxy is approximately 13.6 billion years old. We are just one of about 200 billion or 100 billion stars in our galaxy itself. Our galaxy consists of about 90% of dark matter, the rest 5 and are consistent of dark energy and the entire matter in our solar system. So our galaxy has also been evolving with time, and in about 4 billion years, our galaxy will go on to collide with a nearby galaxy called Andromeda. This slide shows how the collision of a barred spiral galaxy with another Andromeda galaxy will take place, and we will lead in 4 billion years time, we'll go on to merge into a single elliptical rectangular galaxy, which will be called Millimeda, which has been given the name Milmeda. So coming back to our solar system, so our solar system consists of several elements. At the most extremities, we have what is called as the Oort cloud, which is shown as the figure in the bottom left hand side of the panel. So Oort cloud consists of several small icy rocky objects which extend from about 500 astronomical units. To the next slide, on the right hand side in the lower panel, we see the path of an object called Sedna, which transverses beyond Pluto. On the upper slide on the right side, we see the path of several of the various planets in our solar system with respect to the Sedna that transverses across. And then on the uppermost left, we see all the innermost planets that exist in our solar system. So these solar systems exist, inner solar systems exist for about 10 astronomical units, but the entire expanse of solar system of the Oort cloud go as far as 500 astronomical units. So our solar system consists of inner planets which are rocky. So Mercury, Venus, Earth, Mars are the rocky planets. Then we have an asteroidal belt which consists of failed planets or dwarf planets, consist of small rocky bodies ranging from a few tens of meters to few hundred kilometers. Then beyond these rocky planets, we have gas planets which are of typically 10 to 100 times the size of the Earth. We have Jupiter, Saturn, Uranus, and Neptune. Beyond Neptune, we have beyond Neptune again, we have mostly icy, a combination of icy and rocky bodies, which are called Edgeworth Kuiper belt objects. And there are several of them. We will again see a few examples of those. And beyond these, we have a spherical volume or area, whereby again a lot of several swarms of comets that come to our solar system tend to reside or tend to be coming from. Some of these objects have been displaced to that particular distance by the migration of Jupiter and Saturn during the early solar system. They migrated inwards and then they moved outwards, leading to ejection or throwing away of the several these smaller bodies which were initially in the inner part of the solar system, and to conserve the angular momentum, these objects were thrown out to a much larger distance where they currently seem to be coming from. An important thing about our solar system is our solar system seems to have a rather abrupt end at 20 to 50 astronomical units. In a normal planetary system, such kind of an abrupt gap or abrupt end is not seen, and typically it is expected to have to extend to a much larger distance. In this picture, what we see are various inner solar system bodies to scale, which means their exact sizes can be compared over there. So all the planets starting from Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune can be seen. The outer planets have disks around them. The disk of Saturn is a very prominent one with a gap in E and F, between E and D. So inner planets are rocky up to Mars, and then beyond them we have gaseous giants going all the way up to Neptune. So how do these rotate? So most of these objects rotate in the same direction as the direction as the sun spins around. So as you can see, the direction of the planets have been shown in by arrow in the direction in which they are spinning. So all of them are spinning in the same direction as the sun spins. So sun spins on its own axis and also around the galactic center. But for the moment, we are talking of the spin that it makes on its own. So most of the planets are spinning in the same direction as our solar system, as our sun is. This is a very important characteristics that we have to satisfy when we want to elucidate or when we want to form a theory of formation of the solar system. So, then we have to talk about the spin. So not only the planets rotate around the sun, they also spin on their axis. So while most of the planets like Earth, Mercury, Mars, they spin around their own. They spin in a counterclockwise direction. The other planets, the three distinct planets like Venus, Uranus, and Pluto, they have a very different orientation. They are spinning on a very different axis than the rest of the planets. This is again an important constraint that we want to have from the physical characteristics to be able to form a theory when we want to make a theory. So most of the planets again rotate on the same spin axis also, in addition to their axis of rotation. The plane of the rotation of all these planets also lie on more or less within 2.5 degrees to 3 degrees of the plane, except for the Pluto, which we'll see, which is one of the main reasons why Pluto was demoted to a dwarf planet. So in this slide, you can see that most of the planets, Earth, Jupiter, Saturn, Neptune, and Mercury, they are rotating in counterclockwise, but there we have some few oddballs like Venus, Pluto, and Uranus, which have got a very different spin orientation. Venus is rotating in counterclockwise. The axis of Uranus is tilted by about 90 degrees, so it is rotating. Pluto is again, you can see a weird direction of its spinning. So the rocky bodies, the inner rocky terrestrial planets have a rocky surface. All of them are puckered by the impact that these objects have seen. We see it depending upon how they have geologically evolved. These patterns of cratering on them are either visible or are slightly less visible in a geologically evolving planet like Earth. The other planets like Moon, Mars, and Mercury, they are more or less geologically dead, and therefore the impact record of several bodies falling on them during their history from birth till this time. They are more or less recorded at this point of time. But on a planet like Earth, our cratering record is obliterated by the geological evolutions, whereby rivers, mountain chains, and all those volcanoes tend to obliterate the record that is. This is also an important constraint that we want to have when we want to build the theory of origin and evolution of the solar system. So most of the distance are at a very they can be fitted by a very general law, which is called Bode-Titus law. So if you can, so the distance of these objects from the sun can be fitted by a formula which is given by 2 raised to power n times 3 plus 4 divided by 10. Then more or less, if you start from n equals to 0, then as you go on for a different values of n, most of the planets seems to be at that good place. It's just an observation. There is nothing specific about why this should have happened. And from a first order observation of the planets at different around different stars, there doesn't seem to be a particular value or a particular number that we see for our Earth. So, but for our Earth, a very general law, which again hints towards something which we currently don't know, which were discovered by Titus and Bode, and therefore the relationship is named after them. So let's look at the composition. Let's start with the ones which account for most of the mass. So Jupiter accounts for about. So if you leave behind Sun, which constitutes 99.999% of the entire mass of the solar system, the 1% mass or the 0.1% mass that exists in the Jupiter and Saturn is dominantly also composed of the same, more or less of the same composition as that of Sun, hydrogen and helium, but it also has some more elements like ammonia ice, water ice. And inside these two gaseous giants, at the core of them, we expect that a rocky body of the size of about 10 to 15 solar mass, 10 to 15 Earth mass, is at the core of these planets. So because these are gaseous planets, so these have not gone through the stages of differentiation at different points of time. The inner core seems to be crystallizing and is evolving with time. So because of the large amount of size that they have, there is an immense pressure, and therefore the hydrogen has now been crushed or pressed into their liquid metallic state. So at the center of Jupiter and Saturn, we have a liquid metallic hydrogen at this point of time. This all follows mostly from the theory, and observations are a little hard to come by. We have interpreted these sizes and shapes from dynamical parameters that these planets show. For example, the way these planets rotate, the way the attraction goes. So, but there are scars, or there is as such there is no observation, which also doesn't exist even for the terrestrial planets. Then we have other icy giants, which doesn't have rocky core, or the rocky core is expected to be a very, 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 very small size. So they are primarily made up of water, ammonia, and methane ice, and their atmosphere contains only a minor amount of hydrogen and helium. So Uranus consists of about 25% iron and silicate, 60% methane plus water plus ammonia, about 15% hydrogen and helium, while Neptune contains about 20% iron and silicate, 70% methane, water and ammonia, 10% hydrogen and helium. Then, if you look at if you compare their composition and structure, this is how they would look like. These are, the upper panel is scaled to Earth, the lower panel is scaled to Jupiter. So if you look at the upper panel shows all the terrestrial planets that we have, Mercury to Mars. So because these are large rocky bodies, they have enough heat to be able to melt and go through the phases of differentiation, whereby separation of elements or separation of mineral takes place, and therefore we have different layers. The outer layer called crust, then we have mantle, and then finally we have core. So the crust is shown by the black color, the mantle is shown by, the outer mantle is shown by orange or yellow, and then the dark red, and the inner core is shown by dark or the bright yellow color um, in these figures. So as you can see, different bodies have different structure in terms of the size of their mantle, size of their core, size of their crust, which determines their spin orientation, as well as it also gives us an information as to how these planets would currently exist and why they exist uh, the way they are. And therefore, they lets us explore the possibility where there is a possibility of hosting life now or in past, or there will be a possibility in future for these planets to host their life. So, so more or less, the Venus and Earth have a similar size of core, because more or less Venus and Earth are of same size, 0.8 times or 0.89 times that of the Earth. The core is differentiated into upper mantle and lower mantle. In case of our Earth, which is more or less, the upper mantle is slightly bigger in Venus compared to us. And similarly, we can see the same. We can see the similar pattern in the case of Mercury and in the case of Mars. If you look at outer planets, gaseous giants, we can see there is the composition that we described previously. The inner two, Jupiter and Saturn, have rocky bodies at their center, while the outer Uranus and Neptune doesn't seem to have a rocky core. So the inner Jupiter and Saturn, because they accreted 10 to 15 Earth mass of rocky bodies, they grew very massive very suddenly, and therefore they were able to accrete more and more of hydrogen in million or is the main reason why they're so large in size, or they are more massive compared to the other bodies. So most of the mass that came from out that was trying to accrete to the sun was stopped or got accreted into Jupiter and Saturn, because they grew pretty fast in their mass, and then they create a gap, or they accreted all the matter that was coming from the outer solar system towards them. So beyond the rocky core that they have a very large envelope of metallic hydrogen and helium, which is again because of the pressure because of the mass that they have, the pressure is acting to convert this hydrogen into metallic liquid hydrogen at the core, at the just outside them. So Uranus and Neptune are just smaller, Jupiter and Saturn. They're mostly composed of molecular hydrogen, and there is other elements like ammonia and methane on them. If we want to compare how they look like, this is how the core, crust, and mantle would look like in the terrestrial planets and in the outer gaseous giants. So Mars has the largest core. So although Mars is a much smaller body, the core of Mars is much bigger in size than our Earth, but it has a very small inner and outer mantle compared to Earth. This figure shows the comparison between the core, which is shown in gray, followed by inner mantle, which is shown in yellow, and the outer mantle, which is shown in orange color, followed by the outermost covering that we called as crust. So lithosphere exists somewhere, a combination of the black outermost line and somewhere half the way, or to certain depths in the orange region. Outer gaseous giants, again we can see the rocky core of these planets, which are massive to the order of 10 to 15 times, 10 to 15 times of masses in case of Jupiter and Saturn, but very small very small for the case of Uranus and Neptune. The outer beyond, so the mantle, as we call it for Jupiter Saturn, would consist of liquid metallic hydrogen, followed by liquid hydrogen. Then there is a envelope of hydrogen and helium as the gaseous envelope to these planets. So there are several bodies if you want to compare how they look like. So our Pluto or Moon look. So there are satellites to these gaseous giants, and they mimic, or they have a small mini solar systems, just like Sun has several planets. These Jupiter and Saturn, Uranus, they have satellites rotating around them exactly in the same manner as the Sun has planets rotating around them. So if planets are satellites of the Sun, then these gaseous giants have satellites which rotate around them more or less. Again, their orientation and their composition of these satellites of these planets, they give us information, or they hold an important information that is useful to form a theory of the solar system. So Moon is only about 3,500 kilometers, while the satellites of Jupiter and Saturn could be as big as almost twice that size in the form of Ganymede, Titan. So Ganymede, Titan, although they are satellites, they are much bigger than the planets like Mercury and Mars. So this plot shows the typical sizes of these rocky and icy bodies. If we compare the satellites of different planets, then the inner rocky bodies do not have large satellites or satellites. So we have a satellite called Moon. Then Mars has got two captured satellites called Phobos and Deimos. They would again crash into each other at some point in time. Then we have asteroidal belt, which have several rocky fragmented bodies. Jupiter has several satellites. The number is increasing still. Another 50 were discovered for Saturn about a week ago, and the process of discovering more of them of smaller and smaller size is still continuing. So some of the interesting satellites of Jupiter are Io, Europa, Ganymede, and Callisto. Europa and Io host have a composition of methane, liquid methane and ethane, which hold a potential for some form of life to exist. So they are of pretty much great interest in finding the. So then there are several satellites of Saturn II. They are given different names. And similarly, we have satellites for Uranus, Neptune, Pluto, and Charon tend to be rotating around the same barycenter at this point of time. These are exactly to scale. So as you can see, Earth is pretty much much bigger than all the satellites that these planets host. So this is a very crowded slide in which we'll see a magnified version of this figure. This slide tries to show the different satellites all the planetary system has and their position from their stars. For example, in the topmost panel on the extreme left side, we can see Earth, and then we can see the Moon shown as a cyan gray dot. Similarly, in the case of Mars, we can see two Phobos and Deimos, and their relative. These distances are relative for each planet that are shown. Similarly for Jupiter and Saturn and Uranus. In a more magnified image, we can see again the same thing, that Mars has got just one planet, which Mars has got two planets, Earth has got just one planet, Jupiter has got several of them, and they are situated at different size. They show some characteristics like it increases in mass and then goes down in the mass. We currently don't know as to why. There are theories about it, but we are still in the process of understanding how the composition size, if they hold any clue how, when, and these planets form and what is happening to them. Similarly, for the asteroidal belt and for the Saturn and Uranus and Neptune, and for the Pluto. So asteroids are the are rocky bodies that are found between Mars and Jupiter. They are the rocky material that are now trapped in different resonance between Mars and Jupiter. They are materials failed to accrete into terrestrial planets and were not thrown out by the dynamical evolution of motion of Jupiter and Saturn inwards and outwards. So the asteroids are to scale, and the number before them, for example, 1 over here before Sirius, tells that Sirius was the first asteroid to be discovered, followed by Pallas, which is number 2, written over here. Typically, the larger ones were discovered first. Of course, their composition and surface albedo helped them their detection. There are still a few which are currently being discovered, and they are further subclassified into inner zone and outer zone and into their compositional types. Again, they hold a very important information about the dynamical evolution of the solar system, because although they are very, very small bodies, they also seems to show a very great pattern in their chemical composition, as to whether they are rich in carbon, they have a very high albedo, how are their spin axis and orientations are oriented. So when we try to fit a dynamical model of evolution of the solar system, these are the major constraints that have to be satisfied, and therefore they also hold a key to their composition. So composition tells you where they should have formed, and then dynamics lets you move them into their place, which has to be simultaneously satisfied. So this is a summary slide of all that we currently know about the solar system. This is slightly old, and some progress has been made, but most of the characteristics are mentioned over here. This is the relative size of different planets, and as we have said it several times, that Jupiter and Saturn are the most large ones. Their distance, their rotation period, their rotational axis, and number of moons that was known at that particular time. The composition that they are made up of is shown in this particular slide. We have said most of the things, and so outside these, we have what is called a Kuiper belt, named after a famous planetary scientist. Kuiper belt consists of several comets and rocky bodies which tend to which tend to come on an elliptical path close to the sun and then walk away. So comets of different periodicity or non-periodicity also, they tend to come from both the Kuiper belt and the Oort cloud. So Kuiper belt exists beyond the orbit of Neptune from 30 to 50 astronomical units. And Oort cloud tends to exist, gives rise to much. It's a spherical. So while the Kuiper belt is a planar region, the Oort cloud is a spherical symmetrical region around our sun, from which long period planets tend to come from a very from an elliptical path, but along an axis which is tilted much to the plane in which all the planetary bodies are located in our solar system. Recently, we have had also two objects which seems to have come from outer solar system. One was called Unamau, and the other one is called Borisov. So Borisov has been discovered recently. So we have two objects which seems to have come from outside the solar system. So these two regions give rise to comet that we see. Halley would be coming next after 76 years in a few months. So the things that we want to when we want to develop the model for origin and evolution of the solar system, we have to try to explain most of the characteristics that these objects have. So some of the common characteristics are that most of them rotate around the sun in the same galactic plane. Their spin axis is same around them, but we should also be able to explain the anomalies that some of the objects show. For example, the Uranus was tilted by about 90 degrees. Same was the story for Pluto and for Venus. So these are the planets that we have that we have seen in our solar system. But the theory of planetary evolutions should now be able to also be able to explain the diversity that we see in the planet systems around several stars in our galaxy. So Kepler 90 was the first planetary system with 8 number of planets, equal number to our solar system, that was discovered by the NASA's Kepler mission about a year ago. So this slide shows you the comparison between our solar system and the Kepler 90 system. Kepler 90 also has 8 planetary bodies. Some of them again are similar to like our Earth, are rocky. For example, the innermost, like Kepler 90b, 90c, Kepler 90i, they are rocky, while we have outer gaseous giants, much like the solar system, where we have inner rocky planets and then we have gaseous giants. The star is slightly younger in age. It is G0V at this point of time, which is about half the age that our solar system is. It is located about 25-45 light years from our solar system. So although there is a similarity between Kepler 90 and our solar system, there are several marked differences too. For example, most of the planets of Kepler 90 system are located very much close to the sun. So all the 8 planets are located within what would be the orbit of our Earth in our solar system. So all the planets rotate very close to the sun, therefore they receive a lot of heat from that particular planet. But this is the only planet which have got 8 planets as part of our solar system. NASA, the Kepler mission and other observations have led to about 4,000 exoplanetary systems that we currently know. And an old data table of histogram plot of those planets are shown in this plot, and we can see that most of them tend to have smaller number of planets in the range of 1 to 4, and there are very few planets in much larger. But this picture might change as we will continue to discover more planets in the outer regions and solar and in the outer regions. But currently, we only know one planetary system, Kepler 90, which hosts 8 planets equal in number as that of Sun. TRAPPIST 1 is another closer one, which have got 7 planets. What we are really looking for is a planet in the habitable zone, because we are interested in knowing why we exist, and therefore we are looking for a planet which can host life. So, although a star can have a planetary system, if it is very close, if the planetary system of the planet tends to rotate very close to the sun, just like in the case of Kepler 90, then because of the amount of heat that these planets receive, if it is too close, then they are too hot and therefore unsustainable to host life. If they are too far, they are frozen, and therefore there's a difficulty in hosting life. So we want planets to be at the right place and right distance, so that they are able to host life, and therefore they are, depending on the size and the kind of a star, the habitable zone around the star spans an area, spans a volume. For example, for a sun-like star, the habitable zone would extend just beyond the Venus to all the way up to the Mars, or slightly beyond. But for a smaller star or a bigger star, because they are emitting less radiation, the habitable zone is either closer or farther away from them, which is shown in this plot. And we can see the terrestrial planets Venus, Earth, and Mars over here, while some of the planets that have been discovered are also shown in this plot. For example, Kepler 186f lies just at the boundary where if the composition were similar, then the maximum limit where life could be hosted or water could exist on the planet would be somewhere over here. So let's take a quick look at some of the planetary systems that exist in the outer solar system, and how do they compare with our solar system. So TRAPPIST-1, which have got 7 planetary systems. As you can see from this plot, most of these planets around the TRAPPIST star are located very close to the sun, and therefore the chances of hosting them life is very less. If you compare them to the different satellites that the Jupiter hosts, then this is how it would compare. But not all the planetary systems do not have. So there are some planetary systems which have planets in their habitable zone. A simple plot was shown earlier. Now this shows another. So in the TRAPPIST-1 system, we have planets like E, F, G, and H, which are in their habitable zone, but they are icy, and so currently we do not expect life to be hosting on these planets. So if we compare again the TRAPPIST-1 system with our inner solar system, TRAPPIST is a very compact system around a smaller star, and their habitable zone yet hosts these 3 planets. If we compare TRAPPIST with our sun, then this is how the planets are situated. If this is our sun, then Mars, Earth could be situated at this distance, while TRAPPIST, if this is TRAPPIST, then the planets are situated over here. If we compare the same with Jupiter, this is how the major satellites, Io, Europa, Ganymede, and Callisto, are situated with respect to Jupiter. So as I said, there are some planetary systems which have planets in their habitable zone. For example, Kepler 62 system is a K2b type star, is a smaller star of mass about 0.7 times our sun, and therefore its habitable zone is closer to the sun, and therefore there are some planets like 62f, 62e, which are in the habitable zone of that particular star. So comparison between 3-4 exoplanetary systems. So wide diversity, as we are exploring more and more planetary systems, we find that a wide diversity of structure, architecture, composition exists in the planetary systems about different stars, which is what statistically we would have expected, and therefore whether Sun is a typical or atypical planetary system has come to the fore. So it seems that Sun is an exception rather than the general trend that we typically seeing the 4,000 planetary system that we have seen. If you look at several major here, the major stars and planets around us are shown in this. We have an Alpha Centauri here, Sirius around here, Turban over here, and like that. This is again getting more populated with the passage of time. Some of the most similar planets that have been discovered are shown over here. Some of the most probable candidates which have characteristics very similar to the Earth and are situated around a very sun-like star. They are shown over here. For example, we have discovered Kepler 438b, which has the highest similarity index, which consists of the radius, density, escape velocity, and temperature. So if you have radius more or less similar to the Earth, if it has density, which means it has more or less a rocky body similar to the Earth, which would also determine its escape velocity, and if it is in the right distance to have the right temperature for the planets to be able to host, to be able to have water on its surface, and therefore be able to provide a medium or a or a media for life to grow and evolve with time. So these are the 10 most probable candidates that have similarity very close to the Earth that we currently see. The list again is growing with the passage of time. So as you might have heard, Nobel Prize was awarded to three gentlemen, three distinguished scientists. Two of them were awarded the Nobel Prize for their first discovery of uh, a exoplanet orbiting around the Sun solar type star. So, two gentlemen, Michel Mayer and Didier, discovered a planet 51 Pegasi b around a Sun-like star in year 1992. So, if we compare the 51 Pegasi b with our Sun, then this is how our solar system would look like. So, the relative distance from Sun would be like Mercury, Venus, Earth, and Mars. But if you look at 51 Pegasi b, 51 Pegasi b, 51 Pegasi b, which is much bigger in size compared to our own Jupiter. So, Super Jupiter was located at a distance very close to the Sun, even closer than the Mercury that the Sun hosts at. So, this is one of the figures which helped them to establish that a super Jupiter lies close to the Sun, for this distinguished exemplary work, Michel Mayer and Didier were awarded Nobel Prize for this particular year. They shared the other half with James Peebles, who did for the theoretical discoveries of physical cosmology. We will see. We'll have a brief mention about the distinguished work of James Peebles in the next talk. So one of the interests has been to find water on these planets. While the planets are existing in their habitable zone, we have not been able to show whether water on those planets exists. About 15 days ago, first planet with a water vapor has been discovered. With a likely chance of water has been discovered. It is called Kepler K218b. It is about 660 trillion miles away from our solar system. And some important markers like the end of our solar system, the distance where currently Voyager 1 is, the nearest star Alpha Centauri to our solar system exists, is shown in this scalable, distance scalable plot. Again, if we similar to say as to how it would take about 110 light years with the fastest, it is situated about 110 light years from us. So even if we go with the speed of light, it would take about 110 years for us to reach from Earth to the planet where we have found the possibility of water to exist, water vapor to exist. So all this has been made possible by several observations made both either on the Earth or through observatories sent into the outer space. Our quest is on, and a remarkable advancement in the understanding or in the diversity of planetary systems about different stars have been found in last 30-40 years. This plot shows the timeline of major planetary exploration missions that have either taken place or will go in near future, and the supporting organizations for them. So a lot of discoveries were made by Kepler 82, which left in 2009 and just ended its life about a year ago. Gaia and TESS are currently observing major potential candidates, the Cheops and Plato and and Ariel will go in time. Their major objectives have been specified in these. So these would be like a successive missions to further our understanding on specific targets that will hold a major potential to look for habitability on the planets over there. James Webb is another NASA Isha mission, which will go shortly, and we hope to learn a lot about. We expect that in the coming decades, our understanding would improve very, very significantly in the decades because of these planetary missions, both which are currently in progress and due to go in a very short time. So how is that we have been able to make all this progress? So progressively we have been able to capture or build telescopes which have got larger and larger sizes, which are larger in size, and therefore we have been able to develop more sophisticated instrumentation to observe the smaller and smaller objects or smaller variation in the intensity of the star that happens because of the eclipsing of the planets before them. So this plot shows a comparative between different telescopes that are either on the Earth or will be going into the space. For example, Hubble Space Telescope is shown over here. James Webb, which is about 8 or 10 times bigger than the Hubble, is shown over here. The largest that are currently being built and will become operational in very short time, the 30-meter telescope at Mauna Kea and European extremely large ELT will be of this particular size compared to the James Webb that we are floating at this point of time. So with this, I must with this we come to the end of this particular talk. I must acknowledge that a lot of material or the figures that were taken in this talk came from several literature resources, research paper, books, and I acknowledge them for creating such a beautiful view graphs and pictures which I shared with you. With this, I welcome any question that you might have, and if I misspoke something or if I did not say something which was sensible,